Okay, so in this video we're discussing different types of functions. So over the past few days we've looked at and investigated a whole bunch of functions from absolute value to radical functions, trigonometric functions, all those kind of things. And so now we're actually given some situations. And so we're given some examples or scenarios, and which type of function would best represent the scenario being given. So there's some word clues here that help us out, and some of these graphs, I mean, you could look at the situation and say, oh, well, this could actually be this kind of function or this kind of function, but the scenario they give us should give us enough information to give us a clue as to where they want us to go with this graph. So let's go ahead and take a look at letter A, okay, and think about whether it should be a continuous line, meaning will there be any points of discontinuity? Is there a point of which, like, oh, I actually need a break from this and then continue on elsewhere? Okay, so let's think about that. All right, so candle. So situation A here. Each hour, a candle burns down the same amount. Okay, X is the number of hours that have elapsed, and Y is the height of the candle in inches, right? So we think about a candle, you light it, right? Let's say it's a foot tall or 12 inches. And then over time, the candle gets smaller and smaller. If you let it burn all the way till the end, again, who knows how long that actually takes? It's kind of like asking, how many licks does it take to get to the center of a Tootsie Pop? I don't think anyone's going to sit there in front of a candle and watch and verify how long it takes. But mathematically, if we can say, oh, well, that candle burnt for 2 inches in an hour. And so by doing the math, we can figure out how long it will take until it stops burning. But anyway, so it says the x-axis is time, okay, and time in hours. So I'll just put parentheses hours. And then the y is the height, and this is in inches. Okay, so I'm just going to suppose something. Again, I have no idea numbers, but I'm just going to say, let's say my candle is 6 inches tall. I'm just guessing it's 6 inches tall. Okay, at 0 hours of time, my candle is definitely 6 inches tall, right? I haven't burned it, I haven't touched it, so it's going to be 6 inches. But after that first hour, let's say it burns 2 inches. So it goes all the way down to 4. So after 1 hour, it goes down 2 inches. So it's at 4. Okay, let's say another hour goes by. At 2 hours, it burns another 2 inches, so it's down to 2. And after 3 hours, it would burn all the way down to 0. Okay, so and then I have no more candle. That's it. That's all I got. So, but the line I create would be this. And did I say line? That was a Freudian slip. I wasn't meant to say what kind of this is. This is a line, right? And the characteristic of a line, something that we've talked about, is that a line has a very distinct slope. And by distinct, I mean it repeats. It's a constant. The slope of the line never changes. So in this particular problem, my slope was down 2 over 1, down 2 over 1, down 2 over 1. The slope was constant for the entire time. So this is a linear equation. And by definition, linear equations are, in fact, continuous. That's how you spell continuous. There we go. All right, now let's talk about letter B. The letter B, that's funny because it's about a letter. All right, when sending a letter, you pay quite a lot for letters weighing up to an ounce. You then pay a smaller fixed amount for each ounce or part of an ounce. Okay, so what it's saying is, if you don't send a letter, okay, so when you send a letter, the first ounce costs a lot, right? Because like they have to hire someone to send the mail and process it and take it. But once the work is already done, as far as you paying for the work that it takes to get the mail sent, someone delivering it, if the additional ounces that it takes don't take that long because the hard part's already done, you've paid for most of the work, so it's just smaller increases as we keep going. Okay? So, if you send a letter, okay, let's say, again, so the X is the weight of the letter in ounces, so we'll say weight in ounces, OZ, okay, and then the Y value is the cost, and we'll say dollars. Well, actually, it's cents, so I should write C. Okay. And again, I have no context for anything except just to know that if I send something with zero weight, I know it won't cost me anything. But it says up to an ounce, okay, you pay quite a lot. So let's say 50 cents, sure, okay. So it costs 50 cents to send something that's an ounce, okay. But when you get to 2 ounces, the increase won't be as much. Let's say it's just 10 cents, it's 60 cents, okay. And then for every ounce after that, it's just another 10 cents, right? So essentially, I have another line, but this particular line, okay, is increasing, right? Because as the weight of your mail goes up, so should the price of the mail. And it says that you pay a fixed amount, okay, meaning it's going to continue going up for a steady amount. But once you get started, it goes up a steady amount, okay. All right, so now let's go ahead and go to another slide here. Okay, so let's talk about the bus. All right, so a group of people rent a bus for a day. The total cost for a bus is shared equally among the passengers. All right, so schools inherently do this. So if you're an athlete or if you are part of a choir or a band or something like that, you need to rent a bus, right? You pay like $5 and someone does the math for you, how much you need to pay. But if you think about it, that work has to be done somehow. So when we do this, again, let's go number of passengers. So that's X. So I'll put number of passengers, PAS. Okay. And then the Y value is the cost in dollars. So I'll just put a dollar sign there. Okay. So the cost in dollars. So when I'm doing this work, okay, let's say, again, if I don't rent a bus, I pay nothing, okay? But if I have one passenger, let's say the bus costs $500. I don't know. I'm just making it up. So if it costs $500 and I'm the only person riding the bus, that means I have to pay all $500. But if I have someone else come on the bus, that means it's divided amongst 2 people, so that's going to be $250. Right? So it's for 2 people, it's $250 because we split our costs in half. If I were to have 3 people come on the bus, it's $125, right? Because 125 times 3, okay? Actually, 125 times, that's not right. Mr. Schwant, you silly goose. Okay? I don't know what it is for 3, but that's for 4. I should say that. If I have 4 people, it's 125. Okay? And so on and so forth. But notice that there is a definite decline, but it starts here. Okay? So the graph kind of starts here. But another distinctive feature is that my graph doesn't touch the y-axis, right? So because if I don't have anyone, I'm not going to take the bus. I have to have at least one person that rides the bus. Okay, keep that in mind. And notice, no matter how many passengers I have, even if I have 10 or 20 passengers, right, if I divide it evenly, it should always work out. Meaning it will never be 0. Like everyone will just pay a smaller amount, but it's going to continue going in this fashion. Okay, so this looks like a radical equation, and the reason I say that is because the graph is never going to touch the y-axis because I have to pay something if I'm renting the bus. And the graph will never touch the x-axis because if I divide it evenly among everyone who's going, it's never going to be 0. So I'm going to call this a rational function. And again, this is continuous. All right, then the last one, the value of a car. Okay, let's talk about that for a second. Okay, so my car loses about half its value each year. All right, so again, X is time that has passed in years, or time in years. And the Y value is my car value in dollars. So let's say I bought the car, and we'll say it costs $10,000. Okay? So $10,000 car, and again, I just bought it, so it's literally 0 years old. So it's $10,000. Right? It was that amount as soon as I started owning it, which time in years was 0. Then, as the scenario says, after 1 year, it's cut in half. So it's only worth $5,000. After year 2, it's cut in half, meaning it's $2,500. After year 3, it's cut in half again, which I believe, if I'm doing my math correctly, is going to be $1,250. Okay, and so on and so forth. But the distinction between the bus and this car is that my car had an initial value. Okay, so it actually started on the x-axis. On the y-axis. But just like the bus, if I keep going, right, if my car keeps being cut in half of its value, my car will still be worth something. It won't be worth very much, but it will. If I keep cutting it in half, it will still always be above zero. It will never touch zero. So this particular equation is exponential. And this is what we call exponential decay, because it starts off really expensive, but after time it starts dwindling down to almost nothing, but it will never reach nothing. So exponential, and this is also continuous. So that's kind of a breakdown of all the different kinds of graphs that we had, that we talked about, and how they're actually seen in all these scenarios. So I hope this helps, and it will definitely help with the next video I'm about to shoot, where we actually put these in real actual equations in context.